Welcome everyone, this is Hubert F. We take a look at a simple stack buffer overflow that jumps into shellcode. That kind of exploit does work even when ASLR is enabled, but in its naive form it can take a long time to succeed. We will show how to turn those long run times into just a few seconds. The title HiPi is a little pun on PIE and ASLR, and the Greek program used for demonstration. First we explain the actual program and the basic exploit idea. Then comes the main part, the exploit speedup that takes us from days down to seconds. After that we share some practical implementation notes, walk through the actual exploit implementation, and finally show a demo run. The challenge does not give any source code, only a compiled binary. So the first step is to reverse engineer it, for example with Ghidra. What we find is simple: main takes exactly one argument and passes it on to a function called greet. Inside greet, there is a buffer of fixed size, and the argument is copied into that buffer using the string copy function. Two of its properties are important and will shape the entire exploit. First, it stops copying as soon as it hits a 0 byte. Second, it does not check the size of the destination buffer at all. That missing size check is exactly our buffer overflow. When we disassemble greet, we find that there are 72 bytes from the start of the buffer to the saved return address on the stack. So if we overflow the buffer with 72 bytes of filler junk and then write a new value, we overwrite that saved return address. When the function returns, the CPU jumps to whatever address we put there, and we point it at our own shellcode, for example one that runs a cast flag. The binary itself does not use PIE, and the stack is executable, so the program code sits at fixed addresses and the stack can run code. However, ASLR is still active for the heap and the stack, so their addresses change on every run. How can we find this address? An idea is to guess one plausible stack address, hardcode it as the return value, and keep launching the program until ASLR happens to place the stack exactly there. This does work, but it can take ages, and it is essentially what the breachlab writeup suggests. The checksec output shown on this slide confirms the protections, and the long runtime is exactly what motivates the speedup that follows. So let's start from this basic idea of having a shellcode and a fixed value for the saved RIP, which takes many tries until we have the right ASLR values to really hit our shellcode. The key trick for getting more chances for ASLR to hit our shellcode is adding a NOP slide. Instead of requiring the return address to hit one exact byte, we place a long slide of NOP instructions in front of the shellcode. Any jump that lands anywhere inside those NOPs will simply slide down into the shellcode, which gives ASLR a much bigger target to hit. The obvious problem is that the buffer only holds 72 bytes, far too small for a useful sled. The solution is to split the payload into two parts. Part 1 is small and goes into the 72-byte buffer. It is really just the guest return address. Part 2 contains the NOP sled plus the shellcode, and we place multiple copies of it somewhere else entirely. Two options for Part 2 are the program arguments, argv, or the environment, env. By spraying many copies of the sled plus shellcode, we greatly raise the chance that a guest address lands inside one of them. The diagram shows how the payload is laid out across the buffer and the sprayed region. A few practical points. We use a 64 kilobyte NOP slide per copy and spray several of those across the stack through the environment, which increases the chance of hitting one. For the actual action we use cat rather than change mode, because we do not want to modify the flag file, only read it. In shellcode this is done efficiently with the send file syscall, and powntools helps us produce shellcode that contains no 0 bytes, which matters because the string copy function would otherwise stop at the first one. We put the sled and payload into env, and we first clean out the existing environment, because leftover environment variables shift stack addresses around and always get in the way for binary exploitation. As for which fixed return address to guess, it does not matter too much. We use GDB once to see roughly where the sled ends up, and then we wobble the guess a little on each attempt. We also lower the resource limit for core dump size to 0, because writing a core file on every failed attempt would otherwise increase the runtime. Finally, on platforms that have PoundTools installed, the shellcraft module is a convenient way to generate the shellcode without 0 bytes. This slide shows the actual exploit code. First, we are building the shellcode, then spraying it into the environment, then the single GDB run that anchors roughly where the sled lands, and finally the brute force loop itself. The lines we want to highlight are the one that keeps ASLR enabled inside GDB, the offset of 72 for our saved RIP, and the small wobble applied to the guess on each attempt. Here is the exploit actually running. You can see the anchor address printed first, then a series of progress dots while it keeps trying, and finally the hit line together with the captured flag. The run takes about a minute, but it varies a lot, because finding the right address is essentially like winning in the ASLR lottery. A few thank yous. First to BreachLab for the inspiration for this challenge. To Pound.College for teaching us so much about binary exploitation. And to Over the Wire for offering many great Pound war games, plus the well-known Bandit war game. That's me, with my email address and my website. Feel free to reach out with questions.